everyone, today we are talking about lesson 9.4 and the last of our rigid transformations, which are going to be rotations. And this starts on page 120 in your Springboard book. And before we get started there, something I want to talk about is the idea of what is clockwise versus counterclockwise. So if we draw in on this picture here, if we talk about this clock here, and we draw in a y-axis and an x-axis, right? We have this x-axis here through 9 and 3. We have a y-axis through 12 and 6, right? So if we're talking about our coordinate plane, if we're talking about moving clockwise, that is down, right? That's to the right. We're moving clockwise would be this direction because that's the direction that clock's hands move. Versus counterclockwise, which is to the left, or up from our, like at 0, if you want to think of it over here, from 3 moving around, we have that would be considered moving to the left and counterclockwise. Okay. The reason I bring this up is because it's really important to talking about our rotations, because when we talk about a rotation of a new set of points for our Marching Cougars band, the first transformation here appears to rotate clockwise so that we get our first image here, which is this picture here. And then it looks like it is rotating clockwise yet again to get to our next image here. And again, each of these are considered a rotation. And again, it preserves the distance of each point. So these would be considered a rigid transformation yet again. Now, our center of rotation is the part that we're rotating around with our figure. For the most part, we like to talk about these being rotated around the origin, aka 0, 0 on our graphs. Okay. Now, in order to show this rotation, we have some function notations associated with each, and these are really, really important that you keep track of. So if you have a cheat sheet going, you may want to write these down. So a clockwise rotation is going to use the function rule x comma y goes to y comma negative x. So you're going to flip-flop the spot of your x and your y value, and whatever your x value was, you're going to change it. So for instance here, on these points here, our pre-image is at 310. We switched the order of them, and then whatever the x value was is now negative. Again, switch 10 and negative 3. This time the negative 3 became positive 3. And then if you're rotating 0, 0, there's nothing really to be able to switch around on these. It still just stays 0, 0. Now, another type of example they're going to talk about here is when we rotate 180 degrees. Now, a rotation 180 degrees is going to represent just either being clockwise or counterclockwise, because 180 degrees is half of the full rotation of 360 all the way around. And all that's going to happen there is we're going to flip our signs of our values. So again, if we look back here at these original points, 310 becomes negative 3, negative 10. Negative 310 becomes 3, negative 10. So again, we flip the signs, and then 0, 0 stays 0, 0 on that one. Last but not least, there is talk of 90 degrees. This is 90 degrees clockwise versus 90 degrees counterclockwise. What would have to happen? Well, that's where we're going to look at this last point here. And that's going to involve us, again, switching x and y. But what we're going to do when we switch x and y is this time the y value, whatever it was originally, is going to switch signs. Okay, so we're going to see that. They didn't give us any examples there, but this is also something we want to keep track of. All right, so here we have on this next page, on page 121, we have the arrow, and we want to talk about what direction the arrow is going to move after it moves clockwise versus 180 degrees versus counterclockwise. So for part A here, if we rotate this clockwise, what would happen here is it would move to the right. So what would happen to our arrow is that it would also point to the right. Okay. Now, if we talk about rotating this arrow 180 degrees, that's a full-on rotation of our arrow so that it's downward pointing, right? So here is our arrow rotated 180 degrees. And it doesn't matter if we go clockwise or counterclockwise because it's 180 degrees. And again, it's rotated around 0, 0. So notice again, it's kind of that same location from 0, 0 as our original point. Now this one forces the arrow to point downwards when it's rotated that way. Now if we take our arrow and if we put it back to the starting location here, and if we instead rotated it 90 degrees counterclockwise, that means we'd be rotating it to the left. And again, if it's around the point 0, 0, it would be rotated to the left like so. Because again, we went left like this, which means the arrow would be pointing in the leftward facing rotation. Now again, the center of rotation isn't always 0, 0. For instance, here we have a center of rotation here. And what we're asking to do here is describe what kind of rotation would map figure A onto figure B. Well, this figure had to kind of almost like fall to the right, if you will. So it would be considered a rotation 90 degrees clockwise because it went to the right. And then around the point 1, 0 on this case. Now the center of rotation in this next example is going to be a little different. The center of rotation is actually going to be at 1, -2 is going to be our center of rotation. And this time to get this point to go to A to B, we had to move left, which means this time it was a rotation 90 degrees counter clockwise around 1, -2 this time. Okay, so left is counter and right is clockwise. Now moving on here, we are actually going to skip ahead a little bit and we're going to move on from this to talking about, if we skip ahead yet again, I want us to jump to page 124. And the reason I want to jump to page 124 is to talk about our notation. So we've talked about before how translations are how much you're moving your x values, the change in your x values versus how much you're moving your y values. And it's a big T. In reflections, we talk about what line you are reflecting over. So let's say the horizontal line y = 1 is what we're reflecting over. Rotations are going to be represented by a big R. And then they're going to be represented around the point that they're rotating around. Usually it's O for the origin or 0, 0, or whatever point is in the picture. But usually it's O for the origin or 0, 0. And then how much degrees it's moving. Now, 90 degrees, you would think is clockwise, but really this means counterclockwise. And if you have 90 degrees negated, -90, this is actually going to be clockwise. Now you're probably like, why? That doesn't make any sense. Why would -90 not be counterclockwise? Well, it goes to something you're going to talk about in Algebra 2 called the unit circle. And don't worry about knowing the unit circle or anything, but the reason this is because we're starting over here at 0 degrees, and this is where the unit circle always starts here at 0 degrees. And then to move to 90 degrees, you had to move counterclockwise. And to move to 270, or aka -90, you moved clockwise. So this is why it's a backwards thinking situation here when you see -90, because it actually means you're moving clockwise versus moving to 90 degrees, which actually means you're moving counterclockwise, okay? So this next piece here, what we want to do is we want to talk about this in that we want to talk about what does this mean, and then I'll also visually show it. So if we see this R, and then in this case, point O, -90, what we want to talk about here is this means that we are making a rotation 90 degrees clockwise. Because again, remember the 90 and -90 really means clockwise. And then it's around point O here in this picture. So we would be turning our picture so that point O stays in the same spot. That's our center of rotation. And it would move 90 degrees clockwise. So to the right, we see. Now, the second one, though, is asking us to rotate it positive 90 degrees, which really means we are doing a rotation 90 degrees counter. Because again, positive 90 means counterclockwise, aka to the left. And then this time we're using our center of rotation at point C. So what this means is point C is not going to want to change directions here. So what we would do is we would turn it 90 degrees to the left to represent counterclockwise. But then here was point C in the original. Officially, that's the center of rotation we're moving this around. We're hinging it on. So it would look like this would be our picture, 90 degrees to the left. Okay. Now our final one says that we want to move around point A 90 degrees. So again, positive 90 means 90 degrees counterclockwise. And this time again around point A. So we would take this picture and move it to the left, and then here's point A. So what we would make sure we do is leave point A in the same spot, since that's the center of rotation. If you are the center of rotation, you are not moving. Now, just like we had rotational symmetry, reflectional symmetry, we also have rotational symmetry and the angle of rotation. Now, again, a total rotation is 360 degrees. So if you rotate all the way around, that's 360 degrees total. So if you look here, for instance, 360 would bring this back to the beginning. Now, the angle of rotational symmetry is how many times can we turn this so that this picture looks exactly like itself. So if we look here at this isosceles triangle, it will never have a stopping point as we turned it around until it got back to the beginning, until to see it look like itself. It never was able to stop. So we would say you would have to divide that by 1. So really the only angle of rotational symmetry here is the 360 degrees. Now this isosceles triangle, though, still has reflectional symmetry, because we could still write the one line of reflectional symmetry in this, that it was able to be reflectional symmetry, but not rotational. It's just back to 360. Okay, so no rotational symmetry, right? Because it was just 360 degrees. Now our next example, however, it has this equilateral triangle, and notice with this equilateral triangle, if we turn it, one time, and here we are, it would be itself. We could also turn it again a second time, and it would still look like itself. And then finally, this third time, it would be back to the beginning, that it looks like itself. So it was able to be turned 3 times so that it looked like itself. So what we would do is divide this by 3 to get the angle of rotational symmetry, which would be 120 degrees. So angle of rotational symmetry. Now this guy still also has 1, 2, 3 lines of reflectional symmetry as well from the last lesson. Now this rhombus in example C here, we can only turn 1 time so that it looks like itself, and then the next time it's going to look like itself is on the second turnaround so that it's back to the beginning. So on this next one, what we're going to have to do is take 360 divided by 2, because there was 2 turns we could make till it looks like itself again, which means its angle of rotational symmetry is 180 degrees. And with the rhombus, there's actually only going to be 2 lines of reflectional symmetry. So again, kind of comparing what we talked about with the reflectional symmetry versus what we're talking about today with rotational. All right, last but not least, we have a regular hexagon. And a regular polygon, similar to the equilateral triangle, it's another example of regular polygon, is a polygon whose sides and angles all have the same measure. So notice all 6 sides and all 6 angles are the same size here. We can turn this 1, 2, 3, 4, 5, and 6 times, and this is going to look like itself. So the angle of rotational symmetry is going to be 360 divided by 6, so 60 degrees. And we know there's going to be 6 lines of reflectional symmetry we can have drawn in. Now, what this shows us is that there's a shortcut when we have a regular polygon. And if you have a regular polygon, all you're going to have to worry about doing is turning it so that you have 360 divided by the number of sides. So notice when we had polygons that had all the same size sides and all the same size angles, like the hexagon, we just had to divide it by the number of turns. Number of turns, which happen to be the number of sides. Same thing up here. We, in an equilateral triangle where the sides and the angles are the same length, we just had to divide it by the number of sides to get our angle of rotational symmetry. For the isosceles triangle or the rhombus, which are not regular because they do not have the same size sides and angles all the way around, only in this case, like the angles are different sizes, you had to really check for those number of turns in order to figure out what your angle of rotational symmetry is. So it's a really nice shortcut when they tell you something is a regular polygon or equilateral. All right, that ends it for the rotations portion today. Thanks for listening.